Well, hello, CNBT 1311. This is chapter 1 of the book and chapter 1 of your course. Here are all the elements in chapter 1, and we will go through them as best we can. I am not going to read this to you line by line. We're going to go through the highlights. It's up to you, your responsibility to go through everything that's in these chapters. All right, this has to do with the building site. The building site. Buildings do not exist in isolation. They are conceived to house, support, and inspire a range of human activities in response to social, economic, and political needs, and are erected in natural and built environments. So, the building site can make or break a project. All right. Now, there are many factors involved. The topography, natural habitat, what's the purpose of the building, regulatory factors, and we will get into all that. This is important to consider any building site management. In 1987, the United Nations World Commission on Environment and Development. Yeah, wow. United nothing. All right. The framework for a sustainable development basically revolves around 3 points: principles, phase, and resources. Here are all the principles. Reduce resource consumption, reuse resources. That's recycle stuff. But it's redundant. Recycle resources for reuse. Protect nature, eliminate toxics, apply life cycle costing, focus on quality. The phase: planning phase, development phase, design phase, construction, use and operation, maintenance phase, modification, and deconstruction. Sometimes you have to deconstruct before you can construct. Resources: land, materials, water, energy, and ecosystems. Now, these are just a small amount of things that have to go in to a site analysis. You got to get power there. You've got to get people there. You have to have transportation roads going to your project. You have to have laydown area for materials while you're building your project. Everything goes into the planning. All right. Green building. And this is something that everybody wants to talk about. Green building, the greeny weenies. Okay. Green building and sustainable design, they're often used interchangeably, but they're not necessarily the same. Sustainability calls for a whole system. How long is the building going to last? What's the total carbon footprint? We all know that wind energy is the most carbon intensive thing to build, just like electric cars. It takes more carbon to build batteries for 250,000 EVs than it does to supply the fuel for every commercial plane around the world for a year, just for 250,000 car batteries. So, is it really green? Here's something you need to know. LEED, Leadership in Energy and Environmental Design. Boy, that sounds really impressive, doesn't it? They generated a green building rating system. And in 2003, Canada paid for a license for it. So good for the Canadians. All right. The bottom line for a LEED rating system is sustainable sites. It deals with reducing pollution and the activity, not just the construction, but the activity. Water efficiency. How efficient is it? Is the water consumption? energy and atmosphere. Um, encourages increasing the efficiency with buildings and their sites. Materials and resources. You're going to maximize your resources. Um, but your resources and materials, they've got to match the environment in which you're in, right? We don't have a lot of adobe buildings around the Houston area. We got a lot of rain. All right. New Mexico, that's another matter. Indoor environmental quality. Yeah, you can do all the green you want and have a passive building, but people exhaust CO2, they exhaust water, they generate about 1,500 BTUs per hour just sitting on their duff in an office building. So you've got to dehumidify that building. You've got to exchange the air because the air will get bad in the building. Got to make sure that the HVAC system is clean. So there's indoor environmental quality. You can read about all of this, and I expect you to. You'll be tested from everything in the chapter. Innovation and design process. Okay, is it some super duper type of new green building? All right. And there's one more that is probably in your book that's not in this fourth edition, and that's 7. 7 is a 7 is regional priority. Is regional priority. Now, what do they mean by that? It provides incentives for practices that address geographically specific environmental priorities. Well, they had to add that to the 5th and 6th editions so that they could make you buy another book. Well, anyway, so the 7th is regional priorities. That should be in your current book. All right, so there's basically 7. 7 sustainable sites, water efficiency, energy and atmospheric conditions you need to do, how much fossil fuel we're going to use, how much ridiculous wind energy we're going to use, and oh my goodness, out in Sweetwater, the wind isn't blowing too much, and it's getting cold, so this stuff's not going to the grid. Oh, don't we wish we had more natural gas powered power plants online? Sure we do. Well, all right. Again, materials and resources. I mean, if I have to truck material from Minnesota to Texas because I want to build some super duper Captain Billy Whiz Bang building, when I can get a material that will function just as well down here, may not be the same, is it really cost effective for my project? And innovation and design process. That opens up a lot of real estate. It's earth covered structure, all kinds of stuff. All right, and then the regional priority, which is what does your local region want from an environmental standpoint? All right. There's another thing you need to pay attention to. The Architecture 2030 is an environmental advocacy group whose mission is to provide information and innovation solutions in the field of architecture, planning, in an effort to address global climate change. What a boondoggle. All right. The climate's always changing. All right. Its founder, New Mexico architect Edward Mazira, points data from the U.S. Energy. He grabs all kinds of data. You can research this guy, Edward Merzaza, and see if you like his architectural stuff. Frank Lloyd Wright was pushing this back in the 50s. Most of y'all are probably not even old enough to know who Frank Lloyd Wright was, but he coined a phrase, Usonian architecture, which means that the architecture should reflect the environment in which the building is in, including the landscaping and the trees and the solar angles and all that stuff. Claude L. Rollett and Scott, when they were teaching at Texas A&M in the late 60s and early 70s. They did a passive elementary school right across the campus from Texas A&M University. Didn't take much air conditioning or heating because they designed it as a quasi-passive thing long before this stuff got in vogue. Used wind currents and that kind of stuff. Still had to have an air conditioning system and a heating system in there, but it didn't use as much energy as some of the other schools that weren't designed that way. Anyway, the 2030 challenge issued by Architecture 20, it calls for all new buildings and developments to be designed to use half the fossil fuel energy they would typically consume, and that an equal amount of existing building area be renovated annually to meet similar standard architecture. Now that's all well and good. Yeah, you don't want an energy hog for a house or a building. So yeah, we need to be up to date. There are a lot of developments in insulation and vapor barrier, and we'll talk more about the thermal walls and the foam technology that we have now. But the problem is if you insulate and seal up your building or house too much, you don't get fresh air transfer. So then you have to get with your mechanical engineer to make sure you're bringing in enough fresh air to mix with the stale air to dilute it and send it out so that the people don't get sick inside the building. I mean, nobody wants to live inside an igloo cooler, right? You would suffocate eventually. All right. So you'll be reading all about this. Now, site analysis. What happens in a site analysis? A site analysis, there's the definition, is the process of studying the contextual forces. Boy, that sounds really academic, doesn't it? That influence how we might situate a building. Now, if you've got 50 acres and you're going to stick one building on that 50 acres, then yeah, you can orient it pretty much the way you want. You can arrange it so it picks up the prevailing winds and arrange it so that the sun angle hits it just right. But what happens if you're in a subdivision or you're in a small commercial space and you got barely enough room for the number of cars that you have to park? That's right, you got to have parking. And then you're building. Well, you don't have the total freedom to orient it the way that you would want to in some utopian environment. So take some of this with a grain of salt. If you've got the room and can orient it, that's fine. But look at our subdivisions. They're cookie cutter. The houses are stacked right next to each other, and they're oriented where? To face the roadway. All right. So what does that mean? Do you naturally get all the fresh air that's flowing through? No, you don't. So we have to air condition and heat these boxes, which brings us back to our electrical grid and natural gas grid. So there's no free ride. All right. I expect you all to read all of this. Some of this is going to be as exciting as watching paint dry, but remember, you'll be asked some questions from this chapter. And again, I don't want you to agonize over the exam. I haven't even made the exam yet. I've got the exams left over from the 16-week face-to-face classes I taught in 18 and 19, but since we're going through 3 chapters every 2 weeks, it won't be as many questions, I don't think. But we'll see. And if the first exam doesn't work out, we'll back up and retool everything. My goal is to get you successful. Okay? All right. Now, soils. Soils is a big deal. You'll spend a good deal of money. As a former engineer, that was the first thing we did. We would get with, I think McBride Radcliffe was my favorite soils engineering group. They were civil engineers that specialized in soil mechanics. They'd go out to a site and they'd do a core bore well, that's kind of not very straight core bore. They would drill and pull cores at a certain depth out of my site. And so each one of these would be a log, a soil log. And this is not a soils mechanics course. You'll take 4 of those getting your master's in civil engineering. And each one of these samples will be analyzed in the soils lab for compressibility, plasticity, expansion, porosity, et cetera, et cetera. Now, the book says there are 2 broad classes of soils, coarse-grained soils and fine-grained soils. So your coarse-grained include gravel and sand, okay? And then your fine-grained soils are like silt and clay, okay? And they consist of smaller particles, okay? Now, these things are tested by the American Society for Testing Materials, ASTM. ASTM has a testing method for everything from glass to condoms to toilet paper, you name it. If it's a material or a product made, the American Society of Testing Materials has a testing standard for that. Okay. Okay, let's look at the table below. This kind of gives you an idea of, and these are rules of thumb. If you go design your foundation based on this chart, may God have mercy on your soul. You better get a soils analysis from a local registered professional engineer soils analysis company. Okay, highly organic soils are like organic clay and silt and peat. That's got a lot of organic matter, like old dead vegetation and stuff. And that's all peat is. Peat is those big peat bogs and stuff over in Scotland that they go dig the peat blocks out of. They used to heat their houses with peat, and that's what they smoke the barley with to make their scotch. Gives it a really smoky, nasty flavor as far as I'm concerned. But that's just me. So it's unsuitable for support. Let's see. Well-graded gravel is good for, look at the bearing capacity for that, 10,000, 10K, 10,000 pounds per square foot. Silty gravel is 5,000. Clay gravel is 4,000. Well-granulated sand and poorly granulated sand. Okay? Now, this is what my soils engineer would tell me in the soils report. Okay, at this level, this strata will support, I don't know, let's just say 5K. 5 kips. 5 kips. A kip is 1,000 pounds. 5 kips per square foot. All right. So, when I design my foundations, like maybe a spread footing, or let's pretend this is a drilled pier, at a certain depth, I would figure out my building load, because we would have to have already designed the building and figure out how much it's going to weigh and all the live load and dead load, and we'll get to all that later. And then we'll have to figure out what the area of the base of that footing is based on what our soils engineer tells us. So we have our downward force and the resistant force of the soil coming up. All right? All right. Now, the density of these soils is critical, but again, this is not a course in soils mechanics. But you can read through all of this, I expect you to, and get a general understanding of what we're talking about. All right, let's see. Another thing that's very important is what we call the angle of repose. Now, every granular thing, every granular material, whether it's rice or corn, or clay or compacted clay, anything that's granular that flows or can flow has an angle of repose. That just means how high can you stack it? Okay, I'm going to de-engineer, I'm going to de-geek the conversation here for a minute for you. How high can you stack this and it not fall down, not slump and go that way? Well, if it's compacted clay, okay, that'll have a little higher angle of repose. This, everybody knows what an angle is, right? There's the angle, so vertices. Okay, all right. Now, what's this? Oh, dry sand. That doesn't have very much of an angle of repose. And then if it gets wet, it'll tend to slump down. Depends on what kind of clay you have, too, if you don't have erosion control. We have a little talk about that a little bit. Clay, silt, and sand mix. As you know, silt mixed with clay and sand is not going to be as strong as compacted clay or compacted dry sand. Okay, you go to the beach and you get out there where the water is, you start pumping your foot and your foot will start to sink, right? If you move back on the compacted sand that was compacted by the water, you can stand. All right. And then saturated clay, which means it's a wet, fatty clay. Well, we have a lot of different soils down here. We have highly silicon-sided clay, and I told you we weren't going to make this a soils mechanics talk, but we have expansive clays, and so that's why we have a lot of foundation problems along the Gulf Coast. Right, I think we beat that up enough. Another thing you got to worry about with your subsurface is your water table. How high does this water table go? Now, this also is a part of our, what did I do with my, oh, there it is, my soils analysis. So let's just say that they encounter water at, I don't know, 6 feet below the surface. That's going to be in the report, which means when we drill our piers, we're going to have to use caissons, not caissons, but we'll have to use a tube to keep the hole from collapsing when we pour the concrete in. And we want to go below that. Next thing is, how high does that fluctuate? Does the water table go up or does it go down? Okay, so where is that water table? And what kind of water is it? Now, if we're going to put a foundation in here, let's say we're going to put a basement wall, and there's a water table here. Uh-oh, we're going to have a basement full of water. Well, we got to make sure this is high density concrete, and if we're doing a typical wall and slab foundation, we got to put a water stop in there to keep that water from pushing through there. But then how do we build this if this is a normal water table? Well, that means if it's a big commercial project, we'll have to put super giant straws in here called a well pump system to suck this water table down below our excavation while we're building it. Sometimes maybe you've seen these giant water pumps with pipes going in the ground around construction. That's what they're doing. They're pumping that water out. They're sucking out that water to get that water table to drop. And it would drop something about like that. Okay, very expensive. Very, very, very expensive. Best thing to do is stay the hell away from the water table. Okay, sometimes you can't help yourself. All right, topography. What does that mean? Topography refers to the configuration of surface features. Okay, that's what the word means, topography, topographic. All right, is the land flat? Does it slope? How much does it slope? Where does it slope? If, let's just say I have a ditch over here, big bayou, and this is higher than the bank of the bayou, but all of this property slopes to the center of my backyard, and let's say this is the street over here where the rest of the drainage is supposed to go, but my whole yard slopes to the middle of my backyard, I got a big lake back here, right? So before I build anything, I got to come in here and reconfigure the topography. And remember me talking to you earlier about local regulatory things? Well, we have a thing down here called Harris County Flood Control. And when you start changing the topography of a piece of property, making the water go another direction, you've got to have an engineer do all these calculations, and you got to submit that plan to Harris County Flood Control so they can approve it. Now let's just say this was our property, and we would want what? Okay, we would want this to be the highest point, right? And get that slope into the bayou and get that slope into the street. Okay, but if it's not that way when we bought it, we have to get an engineered topographic plan, hire a surveyor, come out there, survey the existing in situ condition. Isn't that a fancy word? Well, you had to get something for your money. Means just the condition it's in when you're there, the original. And then you got to figure out how we're going to change all of this. That is what you got to get approval for from the Harris County Flood Control. Okay, so topography is very, very important. And down here, most of our stuff is flat. But what if we don't live down here? What if this right here is our property that we're going to build something on? And my wife, who must be obeyed, wants the house up here. Well, how much rain off am I going to get coming down the backside of my house? What kind of foundation on this slope? Well, I don't want the house to be like this. We'd be leaning, right? So we're going to make a conditional house that's vertical. Then what do we do with this topography? How do we change it? Or do we build the structure so that it is in unison? Goes back to Frank Lloyd Wright's Usonian architecture. So it fits with the environment of the topography. Okay? This is something you might want to pay attention to. Slope, ground slopes. Okay? You might want to pay attention to that. Ground slopes. That sounds like a good test question, doesn't it? Over 25% are subject to erosion and difficult to build on. Ground slopes over 10% are challenging to use. These are rules of thumb. It depends on your soil analysis and how much runoff you get. Ground slopes from 5% to 10% are suitable for informal outdoor activities. And ground slopes up to 5% are usable for most outdoor activities and relatively easy to build on. Again, your mileage will vary. Okay? But this is how you calculate your percent slope. Okay? That would be your elevation gain, your rise over your run. It goes back to the right triangle. Remember Pythagoras? Oh no, we're not doing math. Don't worry about it. I'm not going to beat y'all up. Trust me. You can take my machine shop math course, and then you can do math. But I think you would like it, because Uncle Mikey's Trig for Poets always gets them through trigonometry. Okay, how about aesthetic in topography? All right. The general intent in developing a site should be to minimize the disturbance of existing landforms. I mean, you don't want to come in here and plow all this stuff down, okay? I mean, you don't. So you might need an earth-covered structure, like old Malcolm Wells did in the late 60s and 70s. He did a lot of earth-covered structures like this. It'd be a house, and it would have 2 feet of dirt on top, and it stayed about 68 degrees year-round inside there. Now, you're not living in a rabbit hole. You can research Malcolm Wells's earth-covered structures if you want. Okay, so we've seen this in the past too. The dugouts on the prairie, they would, dig into a mound and build their cabin inside there. It would stay warm during the winter and cool during the summer, much like an adobe house because it's so thick. Okay. All right, here's an example of a stair step. All right, terracing. All right. And this talks about all that over here. All right. So this would be terracing. All right. So what do we have here? We got a retaining wall. Okay. That's a retaining wall. And since that wall is abutting into the house, we got to worry about moisture, right? What about groundwater? How much groundwater we got around here? How's it going to matriculate into the house? That would be bad. Mommy would be upset. All right. Or elevated structures. Now, anybody that's been on the Gulf Coast knows that all those houses down there are elevated. But sometimes you might want to elevate the structure. Some of those houses along the, the Pacific coast over in California, they're built, they got the little cliff thing here, and here's the ocean, okay? And some of them houses hang out over and they got big columns and piers and stuff, all right? All right, warm air rises, heavier cool air settles into low-lying areas. The temperature in the atmosphere decreases with altitude. Well, no, duh. This talks about the microclimate, okay? If it's near a large body of water. You read through this and get an idea of what they're talking about because, like, if you got a lot of grass, it'll be a little cooler solar radiation, all right? As opposed to if all this was just barren rock where you'd have radiant reflective heat coming back off of it. All right. This all goes back to that LED rating stuff. All right. Plant materials. This is something you want to take in consideration. If you've got some really old trees, you might want to try to orient your building to save them. Or you might have to plant vegetation to decrease the thermal temperature. Wind break, noise break. Problem with trees, though, is what? That root structure. They play havoc on foundations. So maybe if you have to put your slab on grade near a tree, you might want to put in a giant root barrier around that thing, and then underground watering to get those roots to go the other direction. If not, they're going to bust up your slab eventually. Grass and other ground covers. Ivy, climbing ivy on a wall reduces the heat gain on a wall and on a roof. But then again, if you have a flat roof and you've got a lot of vegetation up there, how are you going to get the rainwater off of it? That has to be considered. Trees. Well, we've talked about trees. What do trees do? Trees give us oxygen. They take our CO2 and give us oxygen. They also provide shade. They provide a wind block. So you might want to think about how you orient these things. This is an example of the sun angle across a path. And no, you're not always able to orient your building. But if it's a new construction and there are no trees out there, then when you do your landscaping, you can get with your landscape architecture and kind of say, okay, let's put some trees in here. And where are they going to go? Okay. Depends how much money you got. Okay, trees serve as a windbreak. They define space. They direct screen views. They attenuate sound, knock the sound down. And they improve air quality. And they stabilize the soil for erosion. So we went back up here, and here it is. On this slope here, you might want to plant a bunch of vegetation in here. Okay? You hold that soil. Probably back over here too, because I bet that comes way over there. And if this is an earth covered structure, you're going to want grass up here, or like ivy, that jasmine ivy that's drought resistant. Keep that soil up there. So that's all part of your site planning and your design. But soil stabilization in some places is very, very, very critical. All right, the location, form, and orientation of a building. Here we go. In a perfect world, you'd be able to turn your building to catch the sun angle. Let's see how much time we got. We're at 35 minutes. We'll try to make these 45 minutes. So there probably going to be more than one video for the chapter. But that's all right. All right. Here's a rule of thumb of representative solar angles. All right. Your mileage will vary. And remember, this is the 4th edition. The Earth does not rotate constantly. It wobbles a little bit. So these angles change. So you'd have to get a sun angle calculator that's current, just like the navigational books change periodically as the Earth makes the giant path through space. So Seattle's way up north. So here's your sun angles up there. Compare that to Phoenix. Okay. And here's your at sunset and sunrise. Okay. And that's the altitude at noon. All right. So, yeah, in a perfect world, if you've got a lot of real estate and you can orient your building around there to take advantage of all this, that's fine. But guess what? You may not be able to, right? If you got a major road that delivers transportation to your building site, and it doesn't fit with the super duper greeny weeny idea of orientation, and you got to have places to park cars, then you got to have your structure, and then that structure has to be set back, and you got to be able to get vehicles in if it's a commercial building and around it and all that good stuff. You may just have to do the best you can, which means you have to go back to high-tech materials, okay? So you may get stuck with being down here in Houston and that be the long side of your building that the sun hits instead of the short side of the building. Well, you're just going to have to get over it. That's just the way it works. Now, here's rules of thumb for solar radiation. This talks about how you would orient your building, ideally in cool regions and in temperate regions. And it talks about what a temperate region is. Okay. Hot, arid regions. Are we in a hot, arid region? No, we're in a hot, humid region. Okay. We should be building our houses down here like bungalows. So you'd have somewhat airflow. But guess what? If I've got a house that's built right next to this one, and then right over here on this small lot line, I got another house, you know, and so forth and so on. How am I going to get all this? I'm not, am I? So there again, the site where if this was a giant subdivision, we would have to design the house for the constraints of the site. And we can't expect to have smooth airflow and the right sun angle to eliminate the need of heavy air conditioning, dehumidification, and heating. Again, your mileage will vary, but cool regions have to be oriented one way, temperate regions, rule of thumb, this way, hot arid regions, a rule of thumb this way, and hot humid regions, this is the rule of thumb. Okay? All right. Passive solar design. This is kind of funny. I did a lot of passive solar design as an engineer and architecture student at A&M. So what is passive? Passive means I don't have a heater in there. I don't have an air conditioner, a DX unit, direct exchange unit. A greenhouse is a passive solar design. A terrarium with a glass lid, if I stuck it outside in the summer, is passive solar. Heat goes through the glass, it stays in there. Now this talks about all the stuff that you can do, south-facing wall, if you can actually face it south. And it talks about the constraints for the climate and how much BTUs per square foot per hour. I know this sounds like a lot of geek speak, but it's important. I just said that a human sitting on its butt is going to kick out about 1,500 BTUs per hour normally. Um, how much area for the glazing? Glazing is glass. And then on the floor, you've talked about the thermal mass, the heat collection, what's going to absorb. That's your heat sink, okay? And it talks about different materials for your heat sink, all right? Of course, you're going to need vents and dampers because this thing will heat up and you'll die. And you got to have the exchange of air. You got to get rid of the waste air and then make up with fresh air. Okay. And this talks about the direct gain and indirect gain. So direct gain is defined here. That means that sun's just going to blow through a glass wall. Indirect gain means the sun, the heat energy from the sun, the light energy, is going to hit a thermal mass, like a giant black wall full of water or something, whatever, okay? They had all kinds of, they call them drum walls or trombone walls. It's a thermal mass that soaks up the heat, and then once this gets super, super hot, it emits, it irradiates heat in the house. And then look what we have here. Got to have a vent for cooling. Got to have a vent for cooling. What goes in has got to come out, right? Okay. Y'all don't get scared about this course. All right. All right. Sun space. What's a sun space? Oh, it's like a greenhouse out here. And what's that? That's a wall. Okay. So you might have like a sunroom, so you can go out there and drink your mint juleps and smoke your cigars, because your wife won't let you smoke them in the house, which is good because they stink for people that don't like cigars. Roof pond. I haven't seen too many roof ponds. Seen some commercial buildings with swimming pools on the roof. But this talks about a roof pond where you would heat the water up. This one even shows a movable insulation panel. Wow. And it's the same thing as a drum wall or drum wall. It radiates down, which is kind of silly because where does heat go? Heat rises, right? So if you're going to do something like that, wouldn't you think this would be more efficient over here? Yeah. But hey, what can I say? Some people have done this. Isolated gain. They collect and store solar radiation away from the space. Now, what this means is you've got a heat sink out here, and let's just say it's heating up water pipes, and these water pipes go up in here to a heat storage. And I've seen them as complicated as it's no different than the solar water panels on the roof that heat up the water, and then they go down to a storage container. It's not rocks or anything. This is talking about air, all right? But you can do the same with water. So you heat the water up, pump it down here to a storage collection, which means your floor would also be warm, heated, just like in Colorado and stuff. They have hot water pipes running through their foundations to keep the foundations warm. All right. Solar shading. This is pretty self-evident. All kinds of, you name it. Just drive around and look at different buildings. You got overhangs, you've got louvers, you've got overhangs with louvers, you've got slanted louvers. Some of them louvers even move and they track the sun. All right. All right. Daylighting. You got direct sunlight. And you got skylights, which is a hole in your roof, which you need to really make sure they're maintained or they'll leak. And the problem with these things, if they're not covered and you may get too much solar radiation in the house and you can't cool it, then you got to turn the air conditioner on, right? All right. But read through all your daylighting. This is pretty self-evident. And there's all kinds of ways to do this. You can bounce the light off a wall like this one. There was even a company that had light collection domes, I remember years ago, that would bring down a light pipe, and then have like a light reflection on the ceiling. This would be the ceiling. I don't remember what that company was called. I had one architect that was using those in a building I was a structural engineer on. All right, so we get to precipitation. What do we do with the rain? Where are we at on this? Now we're at 45 minutes. I think we'll go to, let's try to go to an hour. No, let's go ahead and kill it now. And we'll pick up part 2. We'll pick up part 2 here on precipitation, with precipitation.